Our webinar today is titled The Hydrogen Fuel Cells for Small Unmanned Air Vehicles. My name is Chris Worth and I am the organizer for this meeting. We'll begin shortly, but first I have a few housekeeping items to tell you about. Today's webinar is being recorded, and the recording, along with the slides, will be posted to our website in about 10 days. We will send out an email to attendees once those are posted to the site. All attendees will be on mute throughout the webinar, so please submit your questions via the questions box that you should see on your webinar panel. Karen, that's on the next slide there if you want to put that up. We will cover those questions during the Q&A at the end of the presentation. With that, I would like to introduce our DOE host, Pete Devlin, joining us from the Department of Energy headquarters in Washington, D.C. Pete is the Market Transformation Program Manager. Pete, you out there? It's a pleasure to have you. Good afternoon.
I'm here, Chris. Okay, thank you, Chris, and welcome everybody to this webinar. We hope you'll find it informative. We have with us Dr. Karen Schwitter-Lyons. Karen is a section head in the chemistry division at the United States Naval Research Laboratory, where she leads a research program, or several programs, in energy materials and systems. Her present work focuses on using hydrogen fuel cells for long-endurance, energy-efficient unmanned air vehicles, or UAVs, and unmanned undersea vehicles, or UUVs. In 2010, she received the Dr. Dolores M. Etter Top Scientist Award from the U.S. Navy for developing the long-endurance Ion Tiger fuel cell-powered UAV. Dr. Schwitter-Lyons has authored 77 papers in refereed journals and holds 14 patents. She earned a PhD in 1992 in material science and engineering at the University of Pennsylvania for her work on solid oxide fuel cells, and holds a Bachelor's of Science in Chemistry from Haverford College, which she obtained in 1987. So with that, welcome, Karen.
Thanks, Pete. Thanks, everyone. Thanks for your patience getting started here. So you guys have all heard the title and you know who I am. So let me go to the next slide here, slide 4. I work at the Naval Research Laboratory in Washington, D.C., and you can see a map in the upper left corner here. Here we are. Actually, my mouse works. We're right down here by this Bowling Air Force Base, and there's a sewage treatment plant, and we're down here. But we were founded in 1923 by Thomas Edison, who felt, well, he inspired the Navy to form the lab because he felt that the corporate research laboratory was important to the U.S. Navy. And at that time, Thomas Edison, what the culture he brought to the United States was that people had been working in, garages and small labs, and it was hard to industrialize things. And Thomas Edison is really famous not only for the light bulb, but industrializing research. So we were part of that, and that is still our function today. Some of the things we're famous for is we had the first U.S. patents in radar. Of course, the British also developed them. We contributed a lot to the development of geopositioning systems, GPS, and NRL developed the timekeeping system for the satellites. And we were almost first in space, or actually second in space. JPL beat us up. We've done a lot of micro air vehicles. Another thing we're famous for is, believe it or not, permanent magnets were invented here. And that's in everything, electric motors, cell phones, and a lot of enabling technology. The list goes on and on. But another thing I want to emphasize, or not emphasize, or it might be of note, is that we are a federal laboratory, not a national laboratory. So it's not a DOE laboratory, and everyone here is federal employees. So I am a Department of Defense civilian employee. So it's a little different from a Department of Energy lab, but we're still serving the country. So slide 5, the motivation for high-power fuel cell propulsion came out of actually our unmanned air vehicle group here. We have a very good UAV group here, and they actually started doing towed decoys for ships for anti-missile fare. And someone said, well, instead of towing the decoy, let's fly it. And they started flying them, and there was a lot of issues with combustion engines, so they had done a lot of research on electric propulsion, And this Marine guy here, you see him, he's holding Dragon Eye, and this was developed in around the year 2000, and it went out to serve in Desert Storm, and AeroVironment went on to make about 700 kits of these. These are since obsolete, but from that, NRL gained a lot of expertise in electric propulsion. And a lot of the things people like about electric propulsion are here, and this is the same reason why the automotive industry and a lot of industries are moving to electric. Near silent operation, instant starting, increased reliability, ease of power control, reduced thermal signature, and reduced vibration. Some of these are more specific to the military. For instance, reduced vibration. If the airplane's vibrating with an engine, it's harder to catch imaging with the payload. So the advantage of fuel cells is they're higher energy than batteries, and they're higher efficient than small engines. So once you get up to a very large engine, you know, something like a 747 airplane, those are very efficient engines. But a lot of the small ones, and these small airplanes, are pretty inefficient. They're like 10 to 12% efficient. And fuel cells are north of 45%, or even getting up to 60%. So the benefit for small UAVs is they're long-endurance electric unmanned air vehicles. You can do like flights fairly close to the ground. This is a ground level with an inexpensive payload. So the noisier you are, you have to stand off further, and you need to carry a heavier payload. So this lowers the cost and what's called, the military stuff, op tempo. That's operations tempo of missions. So the goal is, in some ways, to say a big UAV mission with a small UAV. You don't have to have a 300-pound airplane. You can do a 35-pound airplane and get the same quality video. So you could say the nanoization and stuff. So we'll move on from that, but that's sort of and I'll return to that in a little bit later. Okay. So hydrogen fuel, you'd say, you know, why is this attractive to the Navy? So compressed hydrogen gas, I'm sure everyone on the phone knows, is now the viable option for the automotive industry. The state of the art is 10,000 psi in development, and this picture on the right here is a Chevy Equinox, General Motors Project Driveway, which is sort of winding down. There's a few cars out there, but that's been out on the roads, and the Toyota Mirai has 10,000 psi hydrogen. The advantages for the cars are same what we have in UAVs. They respond immediately to changes in load and no waste produced, only water. The disadvantages are difficult logistics for remote land operations, but a large and a large storage volume. But this is okay for UAVs more or less because you can make the body wider. So we started this. And this was, goodness, I think it was 2003. So I'm not kidding. 13 years ago. One of my postdocs, and this is, I think Peter's on the phone. There he is, Peter Bowman. So he was my postdoc, and we were working on catalysts for fuel cells. And Peter comes in my office one day and said, "Karen, let's put a fuel cell on an airplane and fly that around." And I was like, "Oh, Peter, that's a terrible idea. That's never going to work." Well, we did it anyway. And right about that time, Protonics Technology Company had come out with this little fuel cell here, and it's about 100 watts. So they're like, "Wow, that's really small. Let's put the fuel cell on the airplane." Well, all this other stuff had to go with it. This is a humidifier that Protonics provided. We developed a radiator here, and we used a paintball tank for hydrogen, a little water pump, and air pumps, and we stuffed it all in this nose. We took a commercial wing from a sailplane, and we built a larger body, and we flew it. Wasn't too successful at first, and then we flew it finally for 3 hours and 19 minutes in 2005. And this was our final group. The big contributors were Jim Kellogg, and Peter really did a lot. So that was great. And basically around that time, remember I talked about Dragon Eye, and the UAV group said, "Great, you flew for 3 hours and 19 minutes, let's put that on Dragon Eye." And I was like, well, it's not going to fit. So we had an idea then to build a new airplane called Iron Tiger. And it was a lovely program, so it was a very simple goal. The goal was 24 hours flight with a 5-pound payload. And 24 hours was sort of just, you know, a day. You go through a night cycle, a day cycle, so very organic goal. And the second thing was a 5-pound payload is about the weight of a day-night camera. So that's about the minimum weight you want for a small UAV. Maybe, you know, some of the little guys, maybe 2 pounds. But 5 pounds is realistic. So we developed this. I have down here a reference to a paper, and at the end of the presentation I'll have a lot of references, and a lot of what I'm talking about has been written up. Not all the specifics, but a lot of it has been. So that's Iron Tiger. So next what I'm going to do is show you a video, And this was made in 2009, so it's 7 years ago now. And the video is 4 minutes and 11 seconds long, so if you want to if you want to take a break. And it's going to show Iron Tiger, and also it was made by ONR, Office of Naval Research, and Office of Naval Research was also investing in General Motors cars, and the end is about General Motors cars, but you can you'll have a good sense of Iron Tiger at the end of the video. So sit back and relax.
Petroleum-based fuels power the machines we rely on every day, from motorcycles to jets, from the massive to the mundane. And although petrol fuels and combustion engines aren't going away anytime soon, the Navy is experimenting with more efficient alternative fuel sources to lessen the Navy's carbon footprint while reducing our dependence on foreign oil. One of those alternative fuels is hydrogen, a fuel source that tries to make this look more like this.
The Navy is interested in hydrogen fuel cells because they offer clean, efficient energy.
The Office of Naval Research and the Naval Research Laboratory are testing zero-emission hydrogen fuel cells. But how exactly do they work?
It's a very simple reaction. It's hydrogen plus oxygen equals water. What we do is, in this case, take hydrogen, and the electrons come off it. It's stripped by what's called the catalyst. And then they go around to the other compartment where there's air, and the electrons recombine with oxygen in the air, and they make water.
Research on hydrogen fuel cells is research into becoming a more environmentally friendly Navy. But there are also important tactical benefits. Take the Iron Tiger, for example.
The Iron Tiger is a fuel cell-powered unmanned air vehicle, and it's designed to fly for at least 24 hours and carry a 5-pound payload.
So ideally that means the UAV can stay out on station longer, or it can travel a farther distance, and it keeps the warfighter out of harm's way and gives them critical information in order to do their job.
And the other feature of Iron Tiger is because it's so quiet, it can fly at low altitudes undetected, whereas versus some of the engine technology, you have to fly at much higher altitudes.
All right, let's do it. Launching in 3, 2, 1, launch. Baby, go.
So there's sort of the consumer side of it, which is very clean, efficient energy. And for the Navy, we take that and turn that into doing missions that we can't do right now with present technology. And so as the Navy moves towards more unmanned systems and they look for high energy propulsion sources, we see fuel cells playing a major role in that.
Iron Tiger is using hydrogen fuel cells to create a tool for the frontline warfighter. But can this technology also be used to make base operations more energy efficient? Marine Corps Base Camp Pendleton says yes.
Describing the fuel cell program here at Camp Pendleton is basically a partnership with GM and us to exercise their vehicles and see how they perform under real-world situations.
They are incorporating 2 of these vehicles into their daily operations. We have no gasoline on board the vehicle at all. We're using compressed hydrogen. In fact, there's no burning or pistons moving up and down or cylinders involved in this vehicle.
Because the vehicle has an electric motor powered by a hydrogen fuel cell, the only emissions it gives off are water vapors. This makes it cleaner than combustion engines. But what about safety?
I'm not a scientist by any stretch of the imagination, but it is a fuel that is much safer than any of the petroleum products that we currently use on the battlefield. The value of this program for the warfighter is the lessons learned that we're going to experience over the next 2 to 3 to 4 years, maybe possibly give those lessons learned to our Marine Corps Systems Command back east, and they could get incorporated in some of the future vehicles that we have that are going to the battlefield.
Whether or not hydrogen fuel cells eventually make it to the battlefield, the research is part of the Navy's commitment towards exploring more efficient fuels that will increase our energy security and help us become better stewards of the environment. For All Hands Television, I'm Petty Officer Brian Covington.
Okay, great. Everyone nice and relaxed. Okay, so that was the video. Now back to some math and, well, at least a chart. So the thing when you're designing an aircraft like this, really weight is an important factor. And here's chart that's from a National Academy Study 2000. And if you look at this, the power source and fuel are typically 35 to 65% of the vehicle weight. And for a small UAV, more like 38 to 48% is a good target, and we'll get into that a little bit more. But that also reserves weight for payloads and things like that. So here, working for NRL, we decided we'd target in on 38 to 48% of the vehicle weight. And our designer, Greg Page, he produced this chart. He's designed many, many vehicles. And he came forward and said, all right, this is how much it's going to weigh. The gross takeoff weight is going to be 35.5 pounds. And here's what you have to do. The fuel cell's got to weigh 2.2 pounds, and it's got to cruise at 267 watts, which means it needs 500 watts. So we all went, that's impossible. You can't do a 1 kilogram fuel cell that produces 500 watts. And then the fuel tank needed to carry about a pound of hydrogen, and that had to fit an 8-pound fuel tank. So that means we needed to hit around 13 weight% hydrogen storage. So we were we were not quite sure what we'd signed up for there, but off we went. So just to emphasize here, the key design point is weight. And also, we tried to develop a commercial off-the-shelf airplane, but we went with that larger frame for Iron Tiger with a large body to carry the fuel tank. So we did a custom airframe. But anyway, this was the dimensions that our designer came up with. And there was a lot of arm wrestling over this, but that's pretty much what we settled on. So here is, for all of you who don't know what a fuel cell system, the components are, here are the general ones. There's the stack, which has all the fuel cell catalysts in it and the chemistry, probably a lot of the more exciting technology in here, but there's key parts, a humidifier to humidify the air, an air compressor, a hydrogen tank, obviously extremely important. Hydrogen ballast, you want to be operating with a high hydrogen utilization, so that's important. There's also a cooling pump, we did liquid cooled, and a heat exchanger, a radiator. So all these pieces had to be optimized to get the system to work well. And the sizing of the system is determined largely by the interrelated properties of the stack, compressor, and heat exchanger. So off we went. There was an interim program between Spider Lion and Iron Tiger. We developed this fuel cell on the left with Protonics. And this was 1 kilogram of 300 watts net. And then we were working with Protonics and said, you know, we need, you're not going to increase your weight budget, but you have to put in another 200 watts. The goal was actually 500 watts, and they did a very good job, and they actually came in overpowered. And this is what it looks like. This is a rail here that our designers asked for so they could slide it in and out of the airplane. So if you took that off, it would have been lighter, but you do have to mount the fuel cell. And this is the stack and the electronics and stuff. And they were able to develop the humidifiers underneath here, a new humidifier design, new air blower, higher power stack, integrated control electronics, and high hydrogen utilization. I want to talk a little bit about the radiator. At the start of the program, the fuel cell could not operate above 60 degrees Celsius, and basically would require 7 times larger radiator than one that operates at 80 degrees C. And here's a chart for the mechanical engineers out there. This is going to seem very simple to you, but me as a chemist, I wasn't as familiar with this. Simple equation or physics equation for looking at heat rejection versus delta T. And essentially, if the fuel cell is running at 60 degrees or below that, if that's its max rating operating temperature, and the external temperature is around 49 degrees C, you literally can't build a radiator big enough to reject heat. So what we want to do is be running the fuel cell up here around 80 degrees or as high as possible, and then if it's hot outside, you can reject heat with a reasonable sized radiator. So this is the square feet of radiating surface. And this became a big deal for us because around 2007 we attempted to build a fuel cell airplane, and it actually came out of the sky. We were flying in the summer and it overheated. We had to ground it. So we learned real quick about the importance of radiators. So an improvement for the Iron Tiger was around this time, for those of you familiar with fuel cells, there was a lot of new fuel cell membranes coming out with higher temperature capability. And obviously the automotive industry has the same chart as we have, so they were pushing for higher temperature membranes, and that helped our program a lot. And we were able to enjoy that higher temperature membranes. So I talked about the cooling system. This is a radiator heat exchanger. This was the initial one on Spider Lion. It was just a flat plate. Peter had actually started with a beer can, but then we went to this flat plate with liquid coolant. we did a lot of modeling, and then we came up with this new radiator, which is very, very high surface area of aluminum, and it is coolant-based. There are a lot of fuel cells that do air-cooled. We do not do that, and I have not studied that extensively. We have pretty much strictly gone down the liquid-cooled path, but we have found that we are able to do fairly lightweight radiators, and combined with the higher temperature, the fuel cells are, as the membranes get better and better, we're able to operate them. The radiator just goes down inside. And generally, when we're flying, we don't even use the coolant loop unless it's over about, unless it's pretty hot out. Usually, we don't even open it. Back to hydrogen. So we did a trade study on hydrogen early in the program, in the Iron Tiger program, and this chart here, we scored them. Unfortunately, it's a little not intuitive, but the low is good in this chart, so we want to look for low scores here. So there's this, we looked at sort of lowest risk, payoff, and here's different technologies. Carbon-wrapped aluminum, so that's a type 3 COPV. Carbon-wrapped titanium. A linerless carbon tank, we looked at 2 different vendors. We looked at cryogenic hydrogen or liquid hydrogen and sodium borohydride. So immediately we found, just by running the numbers, that sodium borohydride, we could not get to a 24-hour flight with sodium borohydride. Again, we needed about 13 weight% hydrogen, so we need about 13 weight%. 24 hours of hydrogen, we need 13 weight% hydrogen, so that pushed us down here. So we went with carbon-wrapped aluminum because we found it was the lowest risk, highest payoff. But if you see here, the purple, here, this chart shows that the cryogenic hydrogen we thought was going to be the highest risk, highest payoff. So, but we didn't bite that off. We wanted to get our airplane flying. So we went with, I wouldn't say lowest payoff, but the carbon-wrapped aluminum was sort of the easiest way to hit our program goals. So we worked on carbon overwrapped aluminum tanks, type 3 tanks, and the company we worked with is Hypercomp Engineering in Utah. We worked on new technologies, metal spinning for custom tank sizes, and new resins with 10% more strength. We developed this is a 22-liter aluminum liner developed by metal spinning, and then you overwrap it. And then it goes into the vehicle fuselage. We developed our own regulators. That was a big issue, was we couldn't really rely on paintball technology. It was just too heavy. And I remember the first regulator I looked at weighed 5 kilograms, so that wasn't going to work. So one of our engineers, Mike Schutte, built a really nice regulator system, and we've really improved a lot on that over the course of time. So we were able to store 500 grams of hydrogen in a 22-liter tank weighing 3.6 kilograms, or 8 pounds. And our regulator was 0.15 kilograms. And this equals 13% hydrogen storage. But I want to note here, the safety factor on this is 1.5. So DOE's transportation goal is 2.25. So the secret largely to our higher hydrogen storage was that we went to a lower safety factor than the automotive is able to go to for DOT. But because we don't work on the highways, we transport our tanks empty, that it's aerospace, even 1.25 is satisfactory for aerospace. So here we go. Yay, we did it. So here's our flight crew. This was a long time ago, 2009. I still see flight, people talking about fuel cell flights, and we still, I think, have the unofficial world records for fuel cell powered flight. There was an 11-hour flight, and then we did a 23-hour flight, and then later I'll talk about this a little bit, a 48-hour flight. This is a picture from our 23-hour flight. We stayed up all night. Some of the engineers we work with, our flight crew, and everyone's names up there. This was done at Aberdeen Proving Ground in north of Baltimore. So that was very successful. And let's talk a little bit about the gross takeoff weight of the vehicle is 16 kilograms or 35 pounds. And I apologize to everyone, I'm switching between pounds and kilograms, but everyone in this field does that, so that's just how it goes. So the total system, including the electronics, the fuel, the coolant, the radiator, everything was about 7 kilograms. This works out to specific energy of about 1,100 watt-hours per kilogram for the compressed hydrogen, 26 hours of flight. And if we look at a comparable lithium-ion battery, it's 200 watt-hours per kilogram. So we're 48 hours of flight, around 300 watts from a 6-kilogram battery. We're or 7 kilograms, or you'd need 30 kilograms of battery to fly for 24 hours at 300 watts, and our whole system only weighs 16 kilograms. You basically can see, unless you have a huge increase in battery to 1100, you just can't get there with a battery. I want to talk a little bit also about hybridization. This is the power profile from our 23-hour flights, and it was an October day, and you can see we started in the morning, and this is climb out. There's high power, and that you can predict how much power you need for climb out. And we got up to around 600 watts. And remember, we talked that the fuel cell, the power, actually they got out to over 600 watts. The target was 500 watts. So we were able to climb out. And then we kind of cruised down here around 300 watts, and there's different things happening. There's winds and gusts, and you're turning and stuff like that, because we're just flying a loop around a base, so we're not going in any direction. So, but here, right here in the evening, was October, and you could see around in the evening, actually a cold front came through. And it wasn't that windy. It was nothing that you would, wake up in the middle of the night or anything in here, but it was windy. You know, it was 20-mile-an-hour winds. And you could just see we stayed here at full power flight for about 3 hours. So if we just had a small battery for hybridization, we would have exhausted that. We really were relying on the full fuel cell to go there. And then here you could see later in the morning it got windy again. And then and the difference was this was a 23-hour flight here, and the one we went on to a 26-hour flight, and it was simply just a less windy day. We just chewed out 3 hours of flight time with this really these fronts coming through. So the system, I talked about this a little bit. So the hybridization, at least for naval platforms, because I do work for the Navy, some of our missions were coming off of ships and we're going inshore, so we could feasibly fly in a headwind the whole way. People would often ask me, you know, how often do you want to be at full power? And I always say we want to be at maximum power for the full mission, because it's possible that we could fly in a headwind the whole way there and then maybe even expend the airplane. So the maximum power of the fuel cell is the maximum power of the system. There might be an opportunity for load leveling. If you can get small, high-power batteries, you could look at hybridization. Our colleagues at University of Hawaii worked with us a little bit on that. We haven't pursued that too actively, you know, wringing out all the efficiency of that, but we prefer that, and this is similar to a car, that the maximum power of the fuel cell is the maximum power of the car. And as you know, also there's a lot of work on catalyst work, and you say, why is this important? And here it's very clear. Here's the weight of our system. It was 6.9 kilograms, and you can see here's the fuel, the cooling system, the fuel cell system. It's mainly in the fuel tank and the fuel, so the fuel part here. And if you went to higher efficiency, this is hours of endurance at 300 watts. As you go from 30% efficient all the way up to, say, 65% efficient, you could see if you just improve the efficiency of the catalyst and the system, you would go from 18 hours of flight up to 36 hours of flight. So we know that, you know, this is relatively old technology here, but as advanced catalysts come out with the same fuel cell system, you could easily increase. We flew around here. You could easily increase, you know, several hours just by swapping out the catalyst and the membranes. So I mentioned also that we had talked about liquid hydrogen when we did that study before, and we said, well, liquid hydrogen looks great. Let's try, if you look at this chart, here's the lower heating values of different fuels, and liquid hydrogen, gaseous hydrogen have the same lower heating value, but liquid hydrogen is 3 times denser than gaseous hydrogen at 5,000 psi, and you don't have that heavy high-pressure storage tank, so the gaseous hydrogen stores at 50 psi. So our engineers got all excited and say, let's do liquid hydrogen. That looks awesome. We're going to do a 3-day flight. So and also pursue this 3,000 watt-hour per kilogram system. So we did it. Yay. Again, another unofficial world record in 2013. This was a 48-hour flight. And you're saying, Karen, didn't you just say it was a 3-day flight? Didn't you design to that? Well, we did, but we only got 2 days. And I'll explain what happened. But it was successful. Here's a picture of the flight crew. I did not go on that crew. I did not go on that flight. And this was, they were so bored just watching the flight all day. They put lights on it and they were filming it and stuff like that. So let me explain a little bit about the LH2 tank design we used, and there's a paper on this we've published, not all the details, but a lot of it, is we have a nested tank. This has insulation in it, and the liquid hydrogen's in here. And we spent a lot of time trying to optimize the boil-off of the hydrogen to the insulation. So, you know, the airplane's always consuming hydrogen, so we want to spend a lot of time trying to match that boil-off rate and get the insulation correct. And you saw we had a lot of flight data on the airplane, so we were able to match that. So there was a vacuum between here with multi-layer insulation, and then designed to the appropriate boil-off volume. And similar designs were looked at for automotive and high-altitude long-endurance UAVs. So what happened was, the reason we got only 2 days of flight, we really overlooked this, and it was just unfortunate. We had done a lot of testing. I showed you that the flight was in April, and we had done all the testing over the winter, and we did it outside for safety reasons. So the Stefan Boltzmann constant has a T to the 4 term, and just going from working in relatively cold degrees to the flight condition, we were flying up here at around we were flying in, it was around 310 degrees Kelvin, or 305 degrees, Kelvin out. Oh, it was right here. So we ended up boiling off a lot more hydrogen. You know, we had done a lot of the tests at lower temperature, and then we flew here, and also being out in the sun with the airplane, with the sun beating on it. It was just, the airplane just got hot. So this was the useful tank capacity, and this was the liquid boil-off, and we just lost a lot more to boil off than we thought. So the options are to decrease liquid hydrogen boil off through increased insulation, but of course that's going to add to your volume and weight. The other thing you could do is fly at here's the ambient temperature. You could fly at very high altitude, so I think this is still attractive for high flyers, but it's still it's tricky. Liquid hydrogen was very, very tricky. So we're not, full disclosure, we are not pursuing liquid hydrogen right now because it was just, the safety issues were cumbersome, and we felt that to basically double the flight, and also to, it was very expensive. The tanks were very expensive, and liquid hydrogen logistics were difficult. We just didn't have any customer who was interested in that. But we have that, we know how to do it, and we could probably improve and get to longer endurance, but we didn't really have a customer, and we felt we understood it, so we kind of have put that aside for now. So the other thing I want to say is that you can really, I would say, enhance your flight tests. There's people come out with flight tests, and I think you're getting the hang of this now. You can really change your endurance by just choosing a nice day. Ideally, because we have a sailplane with large wings, you want cool in the morning, sun in the afternoon, with very low wind. So you could catch thermals. You know, you can kind of trick the flight, because you can just catch thermals, and a big airplane, you could just sort of cruise around with no wind. And also, you could, most days, as I said, if we flew on a day that started around, started sort of cool in the morning and got warm in the afternoon, we wouldn't even need a radiator. So we could have we could have carried a lot more fuel had we just picked our day and not carried a radiator. And for liquid hydrogen, I said choose a cold day, choose a nice cold day, and decrease the liquid hydrogen boil off. The other thing you can do is not carry a payload. So reallocate 5 to 7% of the vehicle payload weight. We carried 5 pounds out of 35. You could reallocate that to fuel or fuel cells. So to some degree, you can kind of trick out the airplane, by taking these little side cuts. But in the end, I think, I work for the Navy. We have to sort of tell the truth and advise the Navy what's going on. So I think we've done a fairly good job understanding where the technology is and trying to make it an all-weather technology. So with that, we decided why not? We'll build our own fuel cell in-house. We have a lot of smart people, and we thought we'd just build it ourselves. So we have built our own fuel cell, and this was our first one. We flew in March 2014. We made a 400-watt fuel cell, and we flew it again on Iron Tiger. Iron Tiger, I got to tell you, is a great airplane. We've done a lot of different payloads with it, and it's a nice airplane. So this is at our flight test at Blossom Point, Maryland, and we 3D printed the plates. We thought that would be a simple way to get the plates to work. And this is sort of what it looks like. We did titanium bipolar plates by 3D laser sintering. We designed the plates oh, I don't have a picture. Here's one of the bipolar plates. This is published. The design is published. So if you want it, there's nothing real special about it. We put them together and assembled them with gaskets, and there you go. And there's our first stack. So we learned how to seal a stack well and how to assemble. The full stack was only showing high cell-to-cell variability and only 80% power, which is why we flew at 400 watts instead of 500 watts. And the problem we ran into with 3D printed plates is the plates really just weren't flat enough. This is a line scan with optical profilometry, and they were just kind of warped. So we were unable to seal everything, and we think we actually got coolant in the hydrogen in the coolant fields in the end. And they're also pretty heavy. I mean, you could see here they're actually pretty thick. The coolant field there, so it's a one-piece part with the coolant in there. And you can read papers on this, but it was kind of neat. But we have decided that we're going to do more what the automotive industry's done, and we have now stainless steel bipolar plates we've designed. And here is a cross-section of our new fuel cell, which we have not flown yet. We're supposed to fly. We should be hopefully flying very soon. And so this is more like an automotive fuel cell. This is a side view where we have straps on it. And looks like a nice stamp plate with metal bipolar plates. And we're looking for a 1.5 to 3 kilowatt fuel cell. This is so that we can fly more tactical missions and go faster. So that's where we are now. So there's other vendors for fuel cell UAVs. These are some of them, and I apologize if I did miss someone. But you guys can look. Energy Ore is one. They're in Canada. Horizon has a lot of stuff out there, and they sell their fuel cells to a lot of people who try out an alternative fuel will fly with a hydrogen fuel cell. They have an air-cooled system. United Technologies has a 1.5 kilowatt fuel cell. We actually work with them on a project with Boeing and ScanEagle. There's a press release on that. You can Google it if you want to find out about it. And there's also, I know AMI Ultra Electronics has a solid oxide fuel cell they put on a vehicle with Lockheed Martin, Stalker, I think. Yeah, Stalker. So these are sort of some of the other companies. I apologize if I missed someone. So some of the research that we did, I wanted to sort of summarize that it wasn't just improving the fuel cells. You want more efficient, effective catalysts, improved hydrogen-oxygen diffusion, higher performance polymer electrolyte membranes. I think you got that out of my talk. Hydrogen storage, higher strength carbons, fibers, new materials for hydrogen storage. Hydrogen production, I think, is important. Biological, electrochemical, solar, can we do it in the field? Another big thing is just increasing the efficiency of the powertrain. We have not worked on that too much, but we've worked on it some. It's just getting higher efficiency motors with improved permanent magnets. We always need more lightweight materials, a light airframe. Aerodynamics, low drag vehicles. Thermal management, I think I convinced you that you need a good radiator. System level modeling, again, this is more powertrain stuff, like with Simulink models. Improved batteries for backup load leveling. Another key thing is lighter payloads, avionics, improved electronics, camera optics, communication systems, and autonomy. So all these things are needed for fuel cell UAVs. The other thing I want to comment on are fuel cells for UAVs economically viable? So I am a scientist, and I am not a business person by any stretch of the means, and I work for the military. So I'll just say what I know. The cost of the lithium-ion battery in Raven, which is the small vehicle used by the military, is about $1,000. This is made by AeroVironment. So how much can a fuel cell system cost, including the hydrogen tank? I don't know, $5,000, $10,000? I don't know, figure it out. And let's say you have $2,000 profit for fuel cells, and for the military, 100 UAVs would be big. This would be maybe a $2,000 profit, and you're still fighting against this $1,000 for a Raven. So you're saying, you need to do long endurance missions. So basically, we need to sell large volumes of systems and develop a cost model where long endurance provides an economic benefit over the battery. And obviously, this is sort of leaning towards a commercial solution, and I don't think it's there yet, but people are certainly striving for it. So I think the question here, business people can answer, is how many UAVs can be sold commercially to get up the profit? And lastly, I kind of alluded to, going nano with airplanes. And I made this slide years ago, and I wasn't going to put it in, and I thought, well, maybe I'll put it in just for comparison. But Global Hawk, which does surveillance, is 700 gallons of fuel, or 2.25 tons of jet fuel per day. And Iron Tiger uses 500 grams of hydrogen per day. So even if we were to make hydrogen from gasoline in the field, with water, with the hydrogen generator, there's 20%. We're still 900 times more efficient. Now this can fly much, much faster. It has way more capability. But you could say, well, maybe you could put up 100 small UAVs and have them communicating and accomplish a lot of what this is accomplishing. So maybe it's a research question, how many small UAVs can be used to replace one large UAV? And then the missions, for the military, it's intelligence and surveillance and things like that. Commercial, communications, people putting up, temporary satellite communications and things like that. So again, I have not been focusing on the business aspects of it, but it's an interesting question of whether you can go small. In this case, this is nano compared to this vehicle. It's an interesting question. And some parting thoughts. I would say the fuel cells are here. If you haven't missed it and don't read the newspaper, I would say UAVs are here. I think we need lower cost fuel cells and low cost practical hydrogen fueling to make these ubiquitous. And here's some references. I'm going to skip over this because you can just Google my name, Google Scholar Me, and this will be, I heard, published in 10 days. And I want to give thanks to my sponsor. This was all funded by the Office of Naval Research. Shell Anderson and Rich Carlin have stood by us. Our team is Benjamin Gould, Rick Stroman in my group, Drew Rogers, Joe McCrell, Mike Schutte, Greg Page, Al Cross, Steve Carruthers, Dan Edwards, and a whole bunch of other people who pulled all-nighters watching this airplane drill holes in the sky. We worked with Doug Wheeler on our follow-on system. The liquid hydrogen fueling station was loaned to us by General Motors. And I also want to give a shout out to Keith Bethune at University of Hawaii, who does a lot of our stack testing and stuff like that. And I am done.
Okay, thanks, Karen. That was great. I really enjoyed it. Because I'm the host, I get to ask the first question.
Oh, great. I haven't looked at the questions, so I thought it would be distracting. So go ahead.
But I was looking at, you were going through your slides, and one of the things caught my eye, and that was this diagram of all the components on slide 13. And you had hydrogen ballast on there. And, yeah, if you can go to it, that'd be great. And I was just kind of wondering, as you were describing it, why would you need ballast? Why, there it is.
Oh, there it is. Well, that's
and more fuel.
Well, I think you need some sort of hydrogen recirculation loop because nitrogen's coming over from the air side and diluting the hydrogen. So there's different ways people do it. I know General Motors did it a different way in their system in the Chevy Equinox, but I'm not going to say how they did it. But there's different ways to do this. I'll just call it hydrogen. You need some sort of hydrogen recirculation system because as nitrogen accumulates, nitrogen will accumulate, but you can still get power out in hydrogen with diluted nitrogen. So you don't want to do a dead-end system and just throw, burp off the hydrogen. We actually did that for the first Spider Lion systems, and we were much less efficient. So going, hydrogen ballast or hydrogen recirculation or other systems, you need some sort of way to recirculate the hydrogen. So maybe I could have relabeled it that. Does that make sense? Is that helpful?
Yeah, when you say ballast, I think of dead weight. So, all right.
Oh, okay,
so,
yeah, maybe that. I'll put hydrogen recirculation. I'll edit that. Okay.
Yeah,
okay. Go ahead.
So going on to some of the questions we got. One of them was fuel tank for gaseous hydrogen. Well, first the mass, and you answered that. 8 pounds on the tank and 1.1 on the fuel. But the pressure, what's the pressure for the gaseous hydrogen? That,
okay. We worked at 5,000 psi hydrogen, and we recently did another study. We haven't published it, but we plan to. I just haven't gotten around to it. Where you could see that it's a fairly large tank, and Iron Tiger has sort of a large body to it. So you could look at, well, if you go to higher pressures, you increase the hoop stress of the tank, and you end up having to add weight disproportionately, so it's not a one-to-one correlation. So we did the study, and we compared it even to the vehicle drag versus, the diameter of the air vehicle, and 5,000 psi is pretty good for airplanes. And the nice thing we did, I'll tell you, and I think this is in our papers, it's not a secret, we didn't have to use a hydrogen compressor. We just would order 6,000 psi hydrogen and just cascade fill the tank. So it's real convenient to work at 5,000 psi. We could go to 10,000 psi, but I think it's very hard to get to 13 weight percent at that loading. But there's still innovations being made, so we still did that, but it was real handy for fueling too because we didn't mess around with compressors or anything like that.
Okay, the next question is, you showed a slide of different storage medium that you tested, and the question is, were there other compounds besides sodium borohydride evaluated for the low pressure option? There it is, slide 17.
Yeah. Well, remember, this was done in 2007. And we looked at sodium borohydride, and then we didn't really look at much else. But I think what you have to, a lot of systems, we continue to look at everything. The nice thing about compressed hydrogen is it has a fairly low system burden, and there's no extra thermal requirements, and there's no extra stuff that goes with it. So essentially, that's what we found actually for cryogenic hydrogen, was it looked real good, and then by the time we started, adding on all this other stuff to get it to work effectively, it sort of a lot of the appeal went away. So we haven't looked at that much stuff, but I mean, people are welcome to look at that, and try it out. I think the challenge is for alternative hydrogen to gas is how you deal with that respond and load. So the airplane hits a big headwind, and you have to dial up, you have to crank up the power, you have to double the power pretty quickly. How are you going to do that? You could get into battery hybridization, but then you have a bigger battery, and then you start adding weight, and then you start saying, oh, let's use compressed hydrogen. So it starts to be a pretty complex problem, but I know a lot of people are looking at it. So long story short, every time we look at it, it's too daunting to look at some of these alternative hydrogen systems.
Right. Well, that kind of gets at the next question, but I'll say it again in case you have any more. And the question is, did you have any problems with fuel cell slow response when you needed higher current or power?
None. Okay. None. It was wonderful. And in fact, I didn't talk about this, but when we flew with Scan Eagle, they were so impressed by the response time with the fuel cell, and they were really happy with it. So it's a very quick response time, and with the electric motor and the torque, it's really has very impressive flight characteristics. Mm-hmm. I mean, our problem was we kind of didn't have a very sporty airplane, so I think we were more limited by our sort of very simple airplane. But if you had a more dynamic, we've flown on more dynamic airplanes, and it's done great.
Okay, so the next question is, did you ever consider direct methanol fuel cells, and why or why not?
Well, I think we talked about that here, right, on this slide with the radiator. We have to run up around 50 degrees C. That's a Navy hot day, and 120 degrees Fahrenheit. And I have been on flight tests where it's that hot on the ground, in southern Maryland. So I mean, this is very real. And again, I had an airplane come out of the sky because it was a July day, and we just got too hot before we really worked on this. So I think the problem with direct methanol fuel cells is that, if the ambient temperature is 50 degrees C, which is very realistic, and maybe even 60 degrees is more realistic, the direct methanol fuel cells are just lower. They operate at lower temperatures. So if you can get I don't know if you can get a direct methanol fuel cell to run up around 80 or 90 degrees C. And also just, inherently methanol has lower, it's right, it's like 6,000 watt-hours per kilogram, unrefined, and you run into the lower efficiency of the fuel cell. So we haven't looked at it that extensively, but it just seems that it's not, it is in the past. But, people can certainly, encourage them to do a quick system study. I think I provided the tools here that people can kind of do a quick study and see what they think.
Okay. Another one is, what are the maximum energy for the total system, everything, balance of plant, the whole works, tank, fuel, pack, and all that? What's the maximum energy on a watt-hours per kilogram basis that this system could reach?
It did reach, this is real, the whole thing, 7 kilograms. That was with the fuel tank, the radiator. Literally, we added in the coolant. It was actually 6.9 kilograms. I made it simpler with 7 kilograms. It works out to 1,100 watt-hours per kilogram.
Okay. Yep.
So with the trick with this is that something like portable power, it's a little different because the airplane has to have sort of a case anyway. Any type of airplane is going to have wings. So a lot of this is the packaging for the fuel cell. A lot of it comes for free. And I think that's where we really win out.
Okay. I think I know what you mean, but
Does that make? Do you want to ask again? So basically, that's real. I mean, these are real things.
free.
I'm sorry, what?
Can you explain what you meant by it comes free?
Oh, well, I remember I used to do a lot of work on soldier power, for instance, compared to a battery, and what would happen was the fuel cell, you'd put it together and then you'd say, oh, this looks great compared to a battery, but then you had to put it in this case, and then the case is what got everyone in trouble, you know, and knocked it down, and it looks like, you know, the packaging, the packaging kind of goes for free. It's the same thing in a car, you know, that you're going to have a car wrapped around an engine of some sort. Right. So I think that when you have something like this where you have a vehicle that exists and you put a fuel cell in it, it's going to look attractive.
Oh, I see what you're saying. Okay.
Sorry, if that's...
Okay, that's all the questions that we received, so you must have covered it really well, and I think you did. So thanks again, and keep up the good work, and I'm sure we'll see you sometime sooner. Hopefully you'll be at the annual merit review, which is week after next.
Right. Okay. Well, thanks, everyone. Thanks for listening. Thanks for your, hope you're enthusiastic as I am about this technology. And also thanks, Pete and Chris, for setting up this webinar, and appreciate DOE.
Very good. Appreciate it, Karen. We'll see you soon. Bye.
Okay.
Thank you, Karen.
Okay. Take
Bye.
care.